What's up? Hey, my name's Noah. I am going to be giving a really weird Unreal Engine talk today about procedurally generating EKGs, which is I know is something you guys have all been wondering how to do your entire life. At the beginning of these, I think you're supposed to do a quick intro yourself. So, my name's Noah. Howdy. By day, I'm an Unreal Engine user. I'm an indie game developer. I've been using it since like 2013, back when it was the UDK. I did freelance 3D generalist work like 5 years, 2015 to 2020. Started an indie game studio in 2023 to focus on edutainment games, so like educational games with an entertainment purpose. And currently working on an emergency medicine game called EKGs. By night, I'm a PA. That stands for either PA, like physician assistant or physician associate, depending on your jurisdiction. I work in some emergency rooms around the DFW area. It's super cool. It's super rewarding. It's a good time. It pays the bills too. So what are we talking about today? This is going to be, again, a weird talk. We're going to be talking about a use case for Unreal Engine 5, which is procedurally generating EKGs for EKGs, the game that I'm currently working on. This is going to be what our end product looks like. Now, how are we going to get there? So my goal for this talk, because I know that y'all probably don't actually care about how to make an EKG procedurally in Unreal Engine, is to kind of take this as a use case for taking a real world complex process and moving that into Unreal Engine, something that Unreal Engine was never meant to do, but like how do you actually make that happen? From a skills point of view, with Unreal Engine, we're going to be doing everything in blueprints and Niagara. On the blueprint side, this is extremely simple. I know one of y'all does blueprints all day, every day. This is going to be way below your abilities. And then for the Niagara side, it's going to be mostly beginner, a little bit intermediate. If anything gets complicated, I will be checking in multiple times throughout the talk. And if anyone's completely lost, just let me know and we'll get you caught up. All right. So step one, what's an EKG? Because we got to actually understand what we're trying to build in Unreal Engine before we can actually build it. I promise this isn't going to be a talk about EKGs, but y'all have to understand it a little bit, and I'm a nerd, so bear with me. We're going to have some fun with EKGs first. Before I keep going on into this, I don't like people to over-explain things to me if I already understand them. So, what do y'all already know about EKGs? Tell me something that you know about them. Yeah, it tells you your heart rate. Yeah, exactly. Yeah, great. Yeah. Yeah, yeah, exactly. Yeah, yeah, perfect. Yeah, 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 exactly. Yeah, exactly. Yeah, flatline, bad. Yeah, yeah. So, all right, EKG or ECG stands for electrocardiogram. Electro means it measures electricity. Cardio means it's in the heart. Gram means it graphs it over time. So electrocardiogram measures electricity in the heart, graphs it out over time. How does that work? So if we're measuring electricity, can you explain the K, please? The K. Oh yeah, sure. So ECG, electrocardiogram. EKG is German, like cardio, like KARDIO. That's where it initially came from. So for some reason, we still all call them EKGs. Yeah. So how does it work? So if we're measuring electricity, we need a way to do that. You put electrodes all over a person. This is like the only Creative Commons image I could find of this. But this old guy's got a little sticky electrodes on him. Each of those is measuring electricity, right? What's it measuring it from? It's measuring it from the heart. So each electrode is checking whether electricity is moving toward that point or away from it, right? And with what magnitude. So each electrode has a direction and a magnitude that is measuring. This is going to be important for our Unreal Engine stuff. And then it draws it out over time. So this is that little line that you're just talking about. It's not a flat line, so this person is not dead. If the line goes up, electricity is moving towards that point, and if it's going down, electricity is moving away from it. So like we've got this guy right here, V1, that's on the right side of the chest. Electricity is usually moving to the left side. So the lines on these big spikes is going down because electricity is moving away from the right side. V6 is over here on the left side, spike goes up, right? So that's all you need to know about EKGs. It's literally like it's measuring electricity in the heart. Flat is bad, and if the line goes up, that means the electricity is moving in the same direction as that electrode. If it's moving down, it's moving away, right? That's it. Thank you for letting me talk about EKGs. It's just the tiny bit of understanding that y'all have to get through the rest of the talk. All right. So we have our basic, our concept, right? Our real world weird thing that we're trying to recreate in Unreal Engine. That Unreal Engine was never meant to recreate. So how are we going to break that down into something we can make? I personally feel that the best way to take a complex real world topic and put it into a game engine is to break it down into the simplest math that makes it work, ideally. Because if you can break it down into the math, you can put it anywhere. Math is the universal language. So earlier, we were talking about our electricity has both a direction that it's moving on average and a magnitude. And if you take a direction and a magnitude and you add them together, what does that make? Anybody know? Do you get the reference? A vector. Yeah, exactly. Yeah. If y'all haven't seen this movie, it looks like a really weird meme, but his name's Vector. That's yeah. All right. So vector, that's something that we can work with. We can use that in Unreal Engine. So now we can hop into Unreal Engine. We've got our little project here. Gonna pop it open. And if we head on over here, I'm gonna hide our EKG for a second. Here's our heart, right? So this is looking at the heart from the front, just like you're looking at someone standing across from you. If we rotate around this way, just to make things a little bit easier to visualize. This is like if you all looked down into your chest and you look down at your heart, if you could see it through your chest wall, this is that same angle, right? So we were talking about V1, V6 earlier, right? That's what each of these arrows is representing. I'm going to turn on some debug tools real fast. These green arrows are each of those directions toward each electrode on the person, right? So we have that as a vector, right? That is just a direction vector, right? It's just a length of 1. And then this blue arrow here, so I'll slow down time so you can see it a little bit easier. This blue arrow is our electricity. That's animated over time. So what we need to do is we need to figure out a way to quantify whether this blue arrow and this green arrow are going in the same direction or opposite directions, and how much, right? Because we already have a magnitude, right? The blue arrow is big or it's small, that's our magnitude, that's easy. But we gotta figure out, does it need to go up or down or somewhere in between, based on, are they in the same direction or opposite directions or somewhere in between, right? Is anyone totally lost so far? No? Y'all are all smart people. This is not that complicated of a process. Okay. So anyone have any ideas of how we can compare the direction of two vectors? Not just compare whether they're in the same or opposite directions, but quantify that. Like, how are we gonna, like, what's a simple math concept we can use? Yeah, yes. I'm so glad someone knew that. All right. How, raise your hand if you've never used a dot product before. It's totally fine if you haven't. Yeah. Everyone used one before? Cool. All right. Well, I'm just going to go through this super quick then. Also just for the recording. So a dot product is just a way to compare two vectors. If you have two vectors that are pointing in the same direction, dot product says maximum. If they're opposite directions, it's at its minimum, and perpendicular is 0, right? So, and if you take vectors with a length of 1, dot product in the same direction is 1, opposite directions is -1, perpendicular is 0, right? And everywhere in between, you just phase between those values. Got a teeny little demonstration here. Again, it sounds like y'all already kind of know how this works, but just in case anyone of the 3 people that will watch this later are interested. So we have 2 vectors here. These are both exactly the same. Because they're exactly the same, both the length of 1, the same direction, our dot product's 1, right? If we rotate one of these vectors, our dot product's gonna work its way down to 0 as they get to be perpendicular, and then to -1 as they're facing opposite directions, and then back up to 0 and back up to 1 as they face the same direction. So if you imagine with our heart, right? If this, say this blue vector, that's our electricity, right? And then this yellow vector, that's towards the electrode. Well, if they're facing exactly the same direction, we should have our line go up maximum amount, right? If they're facing a little bit off, And it should go up like 3/4 of the amount of the magnitude of that vector. Does that make sense? So this is how we're taking our real world concept, our weird EKGs, and we're going to just break it down to simple math. Like dot products are not a crazy complicated thing. Y'all already all know how to use them, right? Again, just for recording, if anyone needs to know how to make a dot product, you literally just pull off a vector, type in dot product, you connect another vector or two, and that gives you your dot product. Easy peasy. Alrighty. I'm going to pull up my little outline here and make sure I'm not forgetting anything, because I promised me so I did practice this ahead of time, but it's been a busy week. All right. Yeah. Alrighty. Yeah, I think that's all we got. All right, cool. So we head back to our little demo here. Here's our heart. And we've got the dot product between the depolarization vector, it's the same as the electrical vector, and V6, which is this guy, right? If we slow down time real fast, you can see it changes over time, right? It also goes above 1 because our blue vector is not a unit vector, right? So without a unit vector, without vectors with length of 1, you can have dot products that max out at less than 1 or at more than 1, right? But this is what we're trying to get to draw our EKG, right? So we have a way now we've built a way to compare the directions of our vectors. We can do the math that we need to, right? Now we got to draw it out over time and make it look cool, right? Because I mean, what's the point of like building this in Unreal Engine if it looks like this? Like this looks stupid, right? So we're gonna jump into Niagara. Raise your hand if you're like a Niagara super user. You've used it a ton. Nice. Okay. I'm really sorry. This is going to be super oversimplified. You're going to know way more. Raise your hand if you've like Niagara's black magic. You have like very little idea how to use it. Yeah. Sweet. Okay. Good. I am not a Niagara super user by any means. This is going to be like beginner/intermediate stuff. If I go through anything and y'all are like, that doesn't make any sense, I'm happy to go back after the talk or whenever and just explain the basics of how this works. Or frankly, she probably can better than I can. Yeah. All right, so we're gonna hop into our Niagara system. We're gonna add an emitter. There are tons you can add. I like to just start with a minimal emitter, right? We're gonna hop in here, name it whatever we want. We're gonna call it EKG for UTD. And our goal with Niagara is going to be to draw our actual EKG line, right? I'm actually going to turn this guy off too so that we're not cheating and showing the end product. And we'll pop in here and we'll show our EKG. Okay, so here's our EKG. There's no lines because we don't have our Niagara set up yet, right? So we need a way to draw lines with Niagara. This is where we're getting a little bit less into like the conceptually, how do you like build, like take a complex topic and more into like, how would you actually make this happen in Unreal Engine, right? It's going to be a little bit more Niagara based. So if we're going to draw a line with Niagara, we need to change our emitter from a sprite renderer, from having a sprite renderer to a different renderer that can draw a line. In this case, we're going to use a ribbon renderer. We're going to turn off our sprite renderer, but we're going to leave it because it's nice for debugging. Because what we want to do is we want to just sample our EKG line numerous times and figure out where exactly it needs to go up, where it needs to go down, where it needs to kind of go somewhere in between. And then we're just going to draw the line between those, right? So with a ribbon renderer, for those that don't use Niagara a whole lot, basically all it's doing is it's taking a bunch of like sample points and it's almost like drawing a spline between them, right? All right, so we've got again, I'm going to pull this up and make sure I don't forget anything. All right, so we've got our minimal emitter. We're going to hop into properties real fast. We're going to turn on local space because we want our emitter to be able to move around in the world and for our line to stay with the emitter the whole time, right? And then we're going to need to spawn a bunch of particles, right? So we could conceptually think of this two ways. We could either spawn particles one at a time going along like as our EKG draws, or we could spawn all of our particles at once and we can just update the position or the opacity of those particles as you know the EKG goes from one end to the other, right? That is way more performant. If y'all want to be nerds about it and talk about how it went wrong doing it the other way, happy to talk about that later. But suffice it to say, way better to just spawn them all at once, keep them all in memory, and you just update them over time. You're not killing particles constantly. So to do that, we're actually going to start in our emitter update. We're going to go spawn burst instantaneous. We're going to spawn a bunch of particles. In this case, we're going to spawn 1024, which I picked for absolutely no good reason. Just like powers of 2. That's going to spawn 1024 particles as soon as this emitter is initialized. We're also going to go into our particle state. We're going to turn off kill particles when lifetime is elapsed because we want our particles to live for forever. We want to spawn them once, and then as long as that emitter exists, as long as that particle system exists, we want that emitter to those particles to always stay alive, right? We don't want them to disappear. All right, so now we're just spawning a bunch of particles. We're putting them all at our emitter position, but we don't want them all to be there. We want to say exactly where each particle goes. We don't even want to say randomly, like kind of spread them around or make a cool line or anything. We want to say this is exactly where this particle needs to go, then this one, then this one, then this one, so we can draw our line with complete accuracy, right? So we're going to go into initialize particle, and instead of simulation position, we're going to go direct set, and then we want to pick from a list of positions, right? Great way to do that is with an array. So we're just going to get an array of positions. If I can get it not to, here we go. Select position from array. We don't want to select a random one. We want to directly pick which one it is. And then we want to go ahead and just put them in order, right? So if we just have an array of positions from 0 to 1023, right? And we have an array of particles from 0 to 1023, then if we just say particle 3 uses position 3, particle 7 uses position 7, makes it super easy. We don't have to think too hard about which particle goes where, right? So we're going to actually set this to our particle ID index, and then we are immediately going to get a compilation error. That is because this is a weird little Niagara thing. If you go into properties here, requires persistent IDs, we need to turn that on. That has a little bit of a memory and performance hit, but it means that your particles are going to have the same ID throughout their existence, right? So particle 7 is always going to be particle number 7. Particle 1000 is always particle 1000. Make sense? That fixes our little compilation error. We can go back to initialize particle. Now, we're picking from our array, like particle 3 has position 3, particle 7 has position 7, and so on, right? Anybody totally lost so far? No? Makes sense? Cool. Awesome. Now we need an array of positions to actually use, right? We could try and calculate this in Niagara. I'm sure our local Niagara super user could probably do that. That's beyond my capabilities. I did it within Blueprints. So if we're going to take a array from Blueprints and push it to Niagara, then we need to use a user parameter. Let's go to this little tab over here, user parameters, and add. And we can add a position array. I've already added one here, very creatively named it array of positions. Then that's something that we can pull, that we can push values from a blueprint into that user variable, and then, or into that user parameter, and then use that in Niagara. So we're going to go ahead and set our variable to that. We're going to say array of positions. And now we are picking from that array what value we're going to, what position we're going to use for each particle. Does that make sense? Everybody? Okay. So if we go back to our little guy here, we've now got these straight lines. Cool. They're dead. Sorry. We're going to bring them back to life. The way we're going to do that, we got to go into blueprints here, and we got to set our actual positions. So to push that value into Niagara, you pull off of your Niagara system, and you set position array. You can do the same thing to set any user parameter, whether that's a color array like we're doing here or any other user parameter. Put in your parameter name, and we're going to use in this local variable local positions, right? To calculate our local positions, now we're going to jump back to our dot products, right? Which thankfully everybody here knows how to use. So for the left to right movement, right? Because we want this to move, this line to move from left to right. Like each particle has got to be one little space further than the other, right? That's our y value, right? And so that's easy to calculate. We're just saying every single particle is just a touch further than the next one. Our x value we're leaving alone because that would mean the line's going out of or into the EKG, and we don't need that to do that. That doesn't make any sense. But our z value is our complicated one, right? Because the line's got to go up or it's got to go down. And so that's where we're going to use our dot products. So we're going to start by taking our electrical vector or depolarization vector. It's the same thing. And we're going to convert it to world space because we want our vectors to be in the same space if we're going to be, doing dot products or any calculations on them, right? Convert it to world space, and then we're going to break it apart, right? So we talked earlier about if you're using dot products, I think it's way easier to deal with normalized or unit vectors, right? Because the length is 1, your maximum is 1, your minimum is -1, and perpendicular is 0. Just makes the math way easier, right? You can add the magnitude back in later. So if we normalize our vector, that turns it into a unit vector. So a vector with a length of 1, right? And if we take our vector length, that's our magnitude, right? And we're just breaking those apart. We'll put them back together later. Now that we have our unit vector, we can take our direction vector, which is also a unit vector, take the dot product between them, and then that's going to give us how much the line should go up or down, right? So this direction vector is from the heart to the electrode. This direction vector is from the heart out to wherever the electricity is pointing. We're trying to figure out, are they pointing in the same direction, opposite directions, somewhere in between, right? And then we're going to multiply it by the magnitude to re-add that variable back in, right? So if, once we know how much we should multiply that by, right, how much we should multiply the magnitude by, whether it's going the same direction, opposite directions, or in between, then we're just taking our magnitude, whether that's 20, 30, whatever, 0, and we're multiplying it back in. So we know how much that line should actually move, right? Does that make sense? Cool beans. Y'all are all going to be experts on EKGs by the end of this. I know that's all what you came here for. All right, then we're going to connect that to our z value. We're going to compile. We're going to play again. And then hopefully we will have brought our patient back to life. We did. Cool. So now our EKG looks like an EKG, right? It looks like a really ugly EKG. It's absolutely hideous, but it looks like an EKG, right? The line goes up when it should. The line goes down when it should. It's not animated, but our real world concept is now actually creating this EKG, right? I'm not going to go through the details of how I made it look prettier, right? If y'all are curious and you want to talk about it, I'm happy to, but that would make this talk way too long. And again, I'm happy to talk about it. It was fun to do. But for now, I'm going to turn that guy off. I'm going to turn this guy, EKG line, back on. I'm going to just show a couple things. We're going to talk about why on earth would we do this in the first place. All right, so here's our actual EKG. If we hop in here, we turn on our sprite renderer again, then you can see really whoops. Turn on our, I wonder if that will make it be colored. It will. Interesting. Well, that's okay. I was going to try and show y'all where the individual dots are going. To show it. Here, let's see if we can make it. Whoops. See if we can make it a little bit bigger. Let's go in here, initialize. I think I'm just setting it right here. From sprite size, let's do 4. Oops. Oh, yeah, okay. Okay. maybe, yeah, 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 yeah. I think those are, yeah, I think those are actually what is colored here. Um, Here, I wonder if I turn the ribbon renderer off. If this doesn't work, it's not a big deal. Nah. Oh yeah, yeah, you can kind of see. Okay, yeah. So ignore the fact that they're all colored. That is a debugging tool for making the EKG do other weird stuff. Um, but you can see these individual dots. Those are dots that are dots that are connected, right? So that's what we're actually calculating, and then our ribbon renderer just ties all those dots together. Does that make sense? Cool beans. All right. So the ribbon draws a line. Yes. Yeah. So if we pop back in here now that I've turned our ribbon renderer back on and our sprite renderer off. Now it's just a steady line, right? So you had all those individual dots, which are easier to see in the big spikes. Ribbon renderer is just drawing like a spline between them, basically, right? Okay. That's the gist of everything that we're going to be talking about today. My last little thing is, why on earth would we do this, right? This is so much work, right? Like this took like so much time to figure out how to do. You got to like learn how to actually like understand an EKG in the first place. You could just draw this, right? And it would just like, just kind of animate it somehow, right? And it would look exactly the same. Player would never know the difference, right? Reason is two things. One, it's super cool. It's super fun to do. I'm a nerd. I like doing this stuff, right? Number two, though, is it lets us do all sorts of cool stuff to procedurally generate EKGs and let the player kind of explore with what's going on. So just as a couple examples, let's say we're going to mess up the heart's rhythm. So suddenly we're in VTAC, right? Heart's just kind of quivering at the bottom. Now our EKG actually shows VTAC, right? Like this is like our heart is just procedurally generating what would happen if that happens, right? Even more nerdy, if we go back to normal sinus rhythm, which is just our normal rhythm, and then we start blocking some arteries, then we'll get these big lumps at the end of each spike, which is actually what we're looking for in the ER when we see someone's having a heart attack, right? Like someone has that EKG, that's a heart attack, right? And then we're like, code STEMI, we gotta like rush them to the cath lab, yada, 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 right? And even nerdier than that, you can have the player put a heart attack anywhere on the heart that you want, right? So like, let's say you want there to be a heart attack over on the right side here. Well, suddenly we're procedurally generating an EKG that looks exactly like that. What if we want to put it on the other side? No problem. We can do that. We can let the player do anything. They can explore, they can break things. There's no limit to what they can mess around with and learn, right? It also, of course, adds all sorts of gameplay possibilities, right? Creating random EKGs and that kind of stuff. In this game, there's a dating app simulator for hearts and EKGs where you're trying to match which one's having the same heart attack and stuff. All sorts of weird stuff you can do, right? So that's why we would actually do this. Anyways, that is pretty much my talk. Thank y'all for bearing with me through this very weird, very strange talk about EKGs and Niagara and blueprints, and letting me talk about educational games and stuff. So appreciate y'all. Yay!